Hi, in this video, we're going to take a look at Pearson correlation with composition data. And I'm going to try to convince you to never, maybe not never, but avoid using Pearson's correlation and even Spearman's correlation when we use composition data. Okay, so I'm going to come out the gates with this quote from the compositions package in R. All right, so the composition package, these guys know composition data, and they say the correlation matrix does not make much sense for compositions. Period. I mean, we really don't need to go any further, but I want to show you why this is a statement of truth. All right, so let's review what composition data is. All right, so composition data is relative multivariate data such as proportions, percentages, and concentrations. Okay, so I'm in a situation where I have, for each observation, I have percentages that add up to 100, or I have fractions that add up to 1, or I have concentrations that all add up to one part per million or something like that. Like every single row of data is proportional to or has been divided by the sum of all the observations or the all the mass or all the volume or something like that. And this comes up all over the place when we're doing data science. And so for example, a good example if you're doing machine learning is that when I do PSI calculations on my predictor variables, those are proportions, right? Those are fractions, those are decimals. And in fact, we really should be treating those as composition data. And in my opinion, different than how the PSI calculations are constructed, but that's for another evening. All right, so since the data points are constrained by a constant sum, standard correlations like Pearson's correlation, Spearman's rank correlation are inappropriate for composition data. Okay, so I'm in a situation, let's say that I'm going to go out, I'm going to do soil samples. I'm going to walk up, scoop up some earth, analyze it. Then I'm going to go somewhere else, scoop up some earth, analyze it, scoop up some earth, analyze it. I'm going to go all across the board, all over the place of interest. And then I'm going to analyze what's going on. Well, really, I don't care about the amount that I scooped up. I care about the proportions of what's inside that soil sample. Okay. And so after I take what I have for each sample, sometimes I'm going to have a sample that, it's just got more dirt in it. Sometimes I'm going to have samples with less dirt. Well, to be able to compare everything, I'm going to divide every single sample I have by the sum of the entire, volume or the entire mass that I've got going on. And then, for each, chemical composition inside the soil, then I'll be able to, compare, where are things more concentrated, where are they less concentrated? That's composition data. And so if we're looking at, let's say, the proportion of males and females in each state, there we're not worried about the number of males, we're not worried about the numbers of females. We're looking at that, the ratio, the proportions, the percentages, at each state. So we can do this with political party, gender, demographics. There's tons and tons of ways that we care about this. All right. So why is it that we shouldn't use Pearson's correlation? Well, first and foremost, we get spurious correlations due to constant constraints. All right. So that constant constraint is because we have the closure is that all of our observations, each individual observations total always adds up to the same value. All right. So think about that. If I have percentages and all the values add up to 100 for each distinct observation. Well, if I look at one observation, I was go, hey, you know what? What if I increased the number? So let's use, male, female. If I was to increase the number or the proportion of males in a location, well, that's a proportion, right? I mean, if to increase the males, the females have to go down. To decrease the male proportion, the female proportion has to go up because it always adds up to 100. Okay, well, that means that I have to have negative correlation, for this to work out. If one goes up, the other goes down. Overall, that means we have a negative correlation. Now, when I only have two variables inside a composition, I will always 100% of the time have perfect negative correlation, -1, regardless of the nature of the data, regardless of if there's a relationship or not. Mathematically, it has to be that way. And so if I'm only considering two political parties, Republican and Democrat, the proportions for those two percentages across counties, across state, across census blocks, whatever I'm looking over, if I only consider those two, then as one goes up, the other one has to go down. It has to work out. We have -1 correlation, perfect negative correlation. All right, now when I have more fields under consideration, then it's not such a tight situation. There is a little bit of flexibility in it, but overall, it still works out. For one variable to go up, another variable has to go down. For one variable to go down, another one must go up. So there has to have negative correlation baked into the system. Or also, the compositions sum to a constant. I mean, this means I can't have independence. That's not possible. Also, we just have the wrong types of values for Pearson correlation. Pearson correlation depends on the actual values, but composition data carries only relative information. Now, we can use log ratio transformations to analyze relationships in a way that respects the relative nature of compositional data, but Pearson and Spearman's correlations do not really respect this structure. So, we have to do some more work on it. Also, another reason to not use Pearson and Spearman correlation is that subcompositional coherence is not there. All right, the idea of subcompositional coherence is that if I have, let's say, I start with 5 variables in a composition, and I get rid of 1, I get rid of 2, I get rid of 5. Any weird combination you can think of. Maybe not 5 out of 5, but I get rid of 4. No, that still doesn't make sense. But if I have multiple variables in my composition, and then I get rid of some of them, and then rescale things to be a composition again, I should get the same results regardless of what subcomposition are under consideration. Now, when I say the same results, that's like relative to each other. We have a little bit of flexibility on it, but like the order and the magnitude of things should be preserved in terms of like the direction of it. That's not going to happen here. I'm going to show you that. I'm going to prove that to you. All right, so Pearson and Spearman correlations can change depending on which compositions are being analyzed by a lot. All right, so now rank-based correlations still fail. So you might go, you know what? I can't use Pearson correlation, so I'm going to use a robust technique. Well, unfortunately, Spearman's correlation, rank correlation doesn't work out for us. All right, so what are some alternative methods? So instead of using Pearson and Spearman correlation, we could use the log ratio transformations. All right, so we could use the center log ratio transformation. So here we take our composition and then we divide all of them by the geometric mean and then take the logarithm. We can do isometric log ratio. So here we take a baseline level, to divide all the others by the baseline, take the logarithm. And then we can also do an additive log ratio. And so this is common in regression situation. We can also use a variation matrix. Now, variation matrix, this is going to measure log ratios between pairs of components, avoiding spurious correlations, but these will always be positive numbers. And so so there's an advantage here, but we don't get like that directional aspect we had before. And, we could also try like robust correlation measures such as pivot, coordinate-based correlations, which respect the compositional geometry. All right, so here I'm going to load some data. This is actually from the help documentation. It didn't print up as well as I would like. It looked a lot better in our Markdown. But here's the information about uh, the data that we're going to use. So we're going to use the hydrochem data. And so here's the raw hydrochem data. I haven't done anything to make it a composition yet. And I can look and I can see the correlations I have. You'll notice I don't have any negative correlations at all anywhere. All right, so now let's go ahead and take, sorry, let's take a composition of our data. And now, after to go through and I close, I convert my data over to a composition, I'm going to go through and take the correlation now. Now, I just said this doesn't make sense, but I want to show you what this is just to compare. Notice all blue across the board. All right. And notice KNACL is a group in MGSRCA S04 are a group. Now things have gotten completely jumbled up. Now here we still have KNA, potassium and sodium chloride are still forming a group, but now we have all these weird things that are popping up that weren't there before. And it's a very different structure looking. So things have switched by quite a bit off of this. Okay. All right, so now here I'm going to go through, I'm going to try to convince you that really Pearson correlation doesn't make sense in the composition aspect. All right, so what we're going to do is I'm going to go through all possible compositions, subcompositions. I'm going to compute the correlation between Na and Ca, okay? And then I'm going to show you the distribution. All right, so if things were subcompositionally coherent, I would get a consistent value off of this. I'm not going to. Okay, so here, let's look at the raw composition value. And I picked this one because it was the largest in magnitude that was in the data set. So about negative 0.88, okay? Now I'm going to run through all of the possible subcompositions, and I'm going to get a range of values. The range of values are going to go from -1, which when I only have the two together, I get the -1, to a maximum of negative 0.89. Okay, it's quite a range if you think about it. And so look at the histogram of all the different values I got. So what I did was I went through all possible subcompositions that I could get. And then I took the correlation between Na and Ca, and doing that over and over and over, I got these values of the correlation. So you can see it's a distribution of values. This doesn't really make sense for us because so if correlation was a useful metric in compositions, I would get like something coherent consistently across all subcompositions, and I'd be able to interpret things easier. But we can see that we can't. All right, so let's say I'm in a situation where I have to do some kind of correlation with my composition data. So one thing that I have learned is that your stakeholders, they're going to learn some statistic concept somewhere along the line, and they're going to want to see something that matches what they already understand. And it's our job to go and deliver to our stakeholders. We have to get them to feel comfortable and confident in our work, even when we have to do some hinky stuff to be able to get the job done. All right, so I'm going to present just some ideas of things we could do. Now, in general, we should avoid correlations with composition data, but let's say that I've got a supervisor or a stakeholder who really wants to see, compositions, or sorry, really wants to see correlations. Now, this could definitely happen, right? Think about like every education, class, tons of education, college classes go over correlation. Psychology classes go over correlation. Correlation is talked about up, down, left, and right in the social sciences, education, in the sciences. So this is well understood by a lot of people, or at least they think they understand it. And so since they feel more comfortable with it, they're probably going to ask us, hey, what is the correlation? Because that's where they're familiar, that's where they can interpret things. They're going to want you to use concepts that they're already familiar with to make it easy for them to interpret. So you could definitely see a situation where a stakeholder that you don't get to talk with directly, maybe a high boss or another office, and somebody in your office is doing the an asset owner is doing the conversations for you, and so they say, oh, let's get correlation going, and then you get yeah, that doesn't make sense. Like what do I do? Oh, we're going to deliver. We're going to use one of these techniques. So the first one is the one I'm telling you not to use. First and foremost, it's a tool in our tool belt. I don't think you should do it, but you can just run correlation with the composition data. And just you have to know, you have to interpret the situation and know that you really can't rely on this. Okay. Now we could also use the compositions function version of correlation. Now, the one that I would recommend would be to use Rob Composition's correlation of composition data. So this function is correlation of composition data. Okay. Now here, what this does is that the output is correlation on that CLR transform data. Now, that's the one where we take all of our composition data, divide by the geometric mean, and then take log ratios. That's the output. The correlation in CLR is the output. That's not how it's calculated. How this is calculated is that it's going to take the ILR. That means it's going to take a baseline. It's going to divide all the components of the composition by the baseline, take the log ratio. Well, you know that something divided by itself, log ratio, is going to have to be ultimately 0. So that's not really a meaningful value. That's constant. All right. Then it does the correlation of like the D-1 composition columns and then converts back afterwards. So it does a back transform to get us the actual results we want. That's the one that I would prefer to use. Now, another thing we could do, we also use the pivot coordinates to achieve this. Now, if we take a look at these two, which I'm going to show in a moment, these give you the same results. A lot of variations in terms of methods within the composition function or composition package correlation function ended up giving me the same results regardless of the structure I had for the data. All right, so here's the first one. This is the one that's just using Pearson's correlation, just run with it, go with it, and do it. Now, if I go and I do the composition version, I'm going to end up getting the same exact correlation, so it's not quite presenting the same way. Oh, did I? Let's see. Oh, it did not print the, okay. These two, for some reason, the code did not give me all 4, it gave me 3. Okay, well, I guess it recognized that there was a duplicate. All right, so these two are going to give me up to rounding off, up to machine accuracy, the same correlations. So it doesn't really matter that I don't see it. Now, these two are going to be different. First and foremost, notice that the Rob compositions one, the one that I recommend, I lost the column names off of this. And so that is to emphasize the transformation. Now, when I pass that over to the core plot function, it went and when it shuffled everything, it re-indexed everything. This is not how the actual data came out. So I want you to pay attention to that, to notice that if I'm going to be working with this function, I need to go in and interpret the columns manually and put labels on things before I do my analysis. Now here with the pivot coordinates, you'll notice that I have fewer columns with pivot coordinates than I have with the others. All right, check this out. See if I can get everything on here. All right, so I've got 14 columns on the original data and on the correlation of composition data, which is what I'm looking at. And if I look at the pivot coordinates, you'll notice I only have 13 columns. Remember, I have a reference level, and that reference level, when I do, when I make that the denominator and take the logarithm, I'm going to get 0 for that column. There's no point in even including it, so it's excluded. All right, so here I've got 13 columns on here to work with for my pivot coordinates. And so just be mindful of that in your interpretation. All right, well, hope you've enjoyed this. Punchline, if you can, avoid using Pearson and Spearman correlations with composition data. If you can't, I recommend that either you do what your stakeholders want and just do it anyway, or the more meaningful interpretation is going to be the Rob compositions version, which is the CLR correlations. All right, well, that's all I've got for you. Life is short. Do math.